Hello everyone, in this video we are going to see an example of the transformation of random variable. Now in the previous videos we had seen a simple examples about transforming the random variable where the functions were invertible. So we used to do this transformation. So we used to take a random variable x and we used to define a random variable y such that y equals f of x, and then given the probability density function of x and the cumulative distribution function of x, we used to find the same for y. So we used to find out the cumulative distribution of function of y, and then we would also find out the probability density function of y. In the earlier examples we had taken a simple function f such that for the given domain of x, this function always used to be invertible for those examples. Hence those examples were easy to compute. I'll give a quick recap of what we used to do to compute the PDF and CDF of y in those cases. So what we used to do was we used to calculate the CDF of x, which is fx of small x, which can also be written as probability of x being less than or equal to small x. And then we used to find out the cumulative distribution function of y such that fy of small y is this probability of capital Y less than or equal to small y. And then we used to replace this random variable y as the function of x. So we used to write it in this way: f of x less than or equal to small y, which would be then converted to this manner: x less than or equal to f inverse of y. Now you can see this is of the same form as that of the cumulative distribution function of x, the CDF of x. So this can also be written as fx of f inverse y. So this used to be the CDF of y, and then we used to differentiate it with respect to small y to compute the probability density function of y, the PDF of y. So this was our general way of working, but in this case this function f used to be invertible for the given domain. Now let's take an example where that isn't the case. So here we have, in this example, let's define a random variable x such that the probability density function of x looks like this. So it takes up the value of 0.5 at x equals minus half. So probability of small x, a probability of this random variable taking the value minus half is half, and it also behaves like a continuous random variable in the range 0 to 1. So it increases linearly from the range 0 to 1, as you can see here. So this probability density function fx can be represented in this manner. So you can see that at the range of like x, small x, lying between the values 0 to 1, it behaves like a linear function and increases linearly like this, and at x equals minus half it takes up the value of 0.5. So here I have represented this in the form of a Dirac delta function. What is a Dirac delta function? I'll give a quick introduction for the Dirac delta function. So Dirac delta function, also written as del x, for example in this case, is a function which extends till infinity at x equals 0. So this goes till infinity, it doesn't meet with the y-axis, and the area under the graph in this case would be 1. So this is what a Dirac delta function is. Now in order to represent the probability in this way, we have represented it as 0.5 here at small x equals minus half. What does this mean? This means that if you just zoom in the value at minus 0.5, it would extend till infinity like this, but the area under this graph would be 0.5. This is 0.5. So we have represented it in this way, which is del of x plus half divided by 2. So we have defined the probability density function for our random variable x, and it is 0 elsewhere. Now let's start with finding the cumulative distribution function of x, as we always used to do. Now to find the CDF of x, we need to do an integration of our probability density function. So we'll integrate it over x. So we will integrate this value dx, and it will give us the CDF of x. So we know that from general observation that after integrating it at this point, so all values after this point to 0 would be half. Since integrating it here would give us the value half, and all the values after this would also be half, since there is no other density present between minus half to 0. So we can say, we can directly map it. So we can say in this case, for the values small x being less than 0 and greater than half, we can say this is already half. Okay, and obviously before that there was no probability, so it was 0. Small x less than half, it was 0. Now after it reaches the value 0, it will increase linearly like this. So we need to integrate it. So if you integrate it, x dx 0 to k, it would behave like k square by 2 plus c. Okay, so if you put a value small k equals small x, it would behave in this way. It would behave like small x square by 2 plus c. Now we know that there is no probability density which occurs after small x is greater than or equal to 1. So that means that capital Fx of 1 would be 1. So let's plug in the value of small x to be 1 here to find out the value of this integration constant. So this would be 1 and this would be 1 square, hence c equals half. So this would behave like this. So if you integrate it x dx, it will become x square by 2 plus the integration constant would be half. So it would behave like this for the range between 0 to 1. So for small x being in the range between 0 to 1, it would behave like x square plus 1 divided by 2. If you want to plot it, you can plot it in this way. So from x equals minus half, it would take the value of half here like this, and then it would increase in a quadratic manner till the value 1. And obviously after reaching the value of 1, it would reach it here, and after this its value is going to be constant, which is 1, like this. So here we have defined the cumulative distribution function for our random variable x. So it looks something like this. This is a straight line. Okay, now let's define a random variable y such that y equals x square. Now in the previous examples, we had taken the domain of x to be strictly greater than or equal to 0. So there was no probability density in our previous example where x could take negative values. This wasn't the case in the previous example. Hence x square acted like an invertible function. Hence we were able to do it so easily. We were able to solve for the cumulative distribution function and the probability density function for y very easily, because x square behaved like an invertible function. But in this case, we have some density present at x equals minus half. So x square won't behave like an invertible function. So we know that the probability density function of random variable x, and we know the cumulative distribution function of the random variable x. So we know this value, which is equal to probability of x less than equal to small x, and we have to find out the cumulative distribution function of y, p of y less than equal to small y. Now you can write it in this way: probability of x square less than equal to small y. But just like in our previous example, we used to do the inverse of this function and we used to write it in this way. We cannot do it in this case because the function f is not behaving like an invertible function in this case. So this would be wrong. So what we would do is we would identify the ranges of x and we would split it in form of a piecewise function, and then we would calculate this value. We will not use the inverse of the function here. So let's see how the value varies. So we know that there are these two values of x. So there are these ranges of x. One is small x being from minus half to 0. Other is small x being in the range 0 to 1. Then there is this range where x is greater than or equal to 1. And then there is this range where x was less than or equal to 2. Less than or equal to half. Okay. Now we can similarly find out the ranges for the random variable x square. So we know the probability density function of x greater than 1 was always 0. That means y greater than 1 would also be 0. So we know that fy of small y, where y is greater than or equal to 1, would always be 1. And similarly, so then we divide the ranges of small y based on the ranges of small x. So just like how the range of small x was divided when CDF of x was computed, we would use these same ranges for small y. So this would be transformed in a way. So for example, this range where small x is less than 0 and greater than minus half, this would be transformed to small y less than being 1 by 4. Similarly, the similar range would be this one, less than half. This would also map to small y being less than 1 by 4. So you see, small y is having two ranges, so it's going kind of symmetrical along with the y-axis, symmetrical to the y-axis. So let's break it down in simpler way and do it. So if we want to compute the CDF of y, we obviously know for sure, since there exists no probability density of x being greater than 1 and x square being greater than 1, because x didn't lie anywhere else. X always lied between minus 1 to 1, so x square is always less than 1. Hence there was no probability density where x square was greater than 1. Hence we know that fy of 1 or any value greater than 1 used to be 1 always. So this will be 1 for any value of y being greater than 1, greater than or equal to 1. Okay, so this was pretty simple because we know there exists no range where the probability here and the probability density of the random variable x here are 0. Hence same would be the case for x square. So the probability density of x square is always between 0 to 1. Rest every other thing would be 0. So the CDF of x square will always be 1 for value of small y being greater than 1. Okay, now that we have sorted this out, let's find its value where y lies between 0 to 1 by 4. So we know one thing for sure, that since x doesn't take any imaginary values, so y cannot be less than 0. So this cannot happen because x can only take real values. Now let's see this range. So this range basically means that small x lies between minus half to plus half. Now we have to find out the cumulative distribution function's behavior where x lied between minus half to half. So we can see that based on the density function of the random variable x, from minus half, where minus half point is not included, from this point till half, we can only see the probability densities which are contributing is the one present in this triangle, since there is no probability density here in this region. So what we would do is we would compute the CDF of x in a different manner now. So we would compute the integral of x dx 0 to k, where obviously k lies between scale is always less than half. We will compute it, and this would come out to be x square by 2 plus some constant c. Now we know that the probability density of this, if you just plug in the value of y here, so it would be y by 2 plus c, and we know that the probability density of fy of y, where fy of 0 would always start with 0, since there is no other value of y behind this point. So if you plug in the value of 0 to y, you can equate this to 0. Hence this is nothing but c plus 0 is 0. So in this case c equals 0. So for this case it would behave like y by 2. Now let's see what happens when the value is 1 by 4. So let's say y equals 1 by 4. So this will only happen when x equals minus half or x equals plus half. And we know that when x equals minus half, it used to take up the value p of x equals minus half used to be half. So it would add half to your cumulative distribution function. So let's see what value would it take. So you see that if you draw fy of y, it would increase linearly like here y by 2, and then at this point, which would be, since this is 1 by 4, this will be 1 by 4 by 2, which is 1 by 8. So this point would be 1 by 8, and if you add half to it, then you would get this point where the CDF of y would take up the value of this. So this is nothing but half plus 1 by 8. So this was 5 by 8. So it will take this value. As there was no other density at x equals plus half, because the range, this interval was very thin, so its value was 0. So this pointed to 0 and x equals minus half pointed to half. So we just added half to the boundary of this CDF. Hence this value was 5 by 8. Now we will compute the value of y being in between 1 by 4 to 1. So this would also be straightforward, because here the function f, it would behave like an invertible function, because there was no other negative value here between minus half to 1, minus 1. So we would again integrate x dx, and this will be small x square by 2 plus c. Now we know that the value at y equals 1 would be 1. So we know this will occur. So the rightmost boundary of this should match to 1. Hence, if we plug in the value of y here, y equals x square, so this is nothing but this, and if you put y equals 1, it would be half plus c equals f of y, which is 1 here. So c is half in this case. Hence, when the range of y is from 1 by 4 to 1, this would behave as y by 2 plus half, or you can say y plus 1 by 2. So this will behave like this. Okay, now let's draw the graph and see its realization. Y and fy of small y. So from y varying between 0 to 1 by 4, it will increase linearly with the slope of half. So this is 1 by 8 and this is 1 by 4, and it won't include this point. And then at y equals 1 by 4, it would shoot up to 5 by 8. And then again it would increase linearly till it reaches the value 1. And after the value of 1, it would be constant at 1, like this. Hence, this is how the CDF of f looks like. Now, to find out the probability density function fy of small y, all we need to do is we need to differentiate this value, this function. So what would this look like? So we know we will when we are differentiating it in this range where y lies between 0 and 1 by 4, the differential of y by 2 is half. So this is half with respect to small y. So if we just draw it parallelly, we can say that this value is half, and it will be here slightly before the value 1 by 4, and at the value where y equals 1 by 4, this would take the form of a Dirac delta function. So this would behave like this: del of y minus 1 by 4 divided by 2. So it would shoot up to infinity, but the area under this ultra thin strip would be half. And then for the range where y is between 1 by 4 to 1, if you take the differential of this is also half again. So this will be half for y between 1 by 4 to 1, and this is 0 elsewhere. So you can just continue this one till it reaches the value 1. So this is what the probability density function of y looks like in this example. So in this video you have learned how to transform a random variable in such a case where the transformation function is non-invertible. I hope you like this video. Please like, share and subscribe to the channel. Thank you for watching.